Hello everyone, welcome back. In the last class, we looked at the compact schemes and we saw that for a given stencil, the compact scheme gives you better accuracy compared to the regular schemes, for example, the central differentiating, and we derived the compact scheme for the 3-point stencil, and that was the 4th order accurate scheme compared to the 2nd order accurate scheme that you see in central differentiating. And we also noted that for certain derivatives, the compact scheme give you better results, better approximation of the derivative compared to the central differentiating scheme. Of course, like we have this one sided formulation, you can also have the one sided formulation for compact scheme. So, the approach remains the same. You write your the left hand side in terms of the implicit points, your phi I primes, phi I minus 1 primes, phi I plus 1 primes, and the right hand side are the explicit points where you have the functions available. Basically, create a matrix, do the matrix inversion and solve it to get the value of all the derivatives at the same time, okay, not sequentially, but all the derivatives in a grid will be calculated at the same time. Okay. That is why it is called the compact scheme. So, today we will see that we can basically increase the stencil size and we can basically get more higher order compact schemes. Okay. This is also consistent with the thought that we have in the last class, that recall that we have discussed that if you want to get the nth order derivative, you need n plus 1 stencil point and at least n Taylor series, right. So, for example, if you want to get the first order derivative, you need at least 2 stencil point and at least 1 Taylor series expansion, right. But we also said that you can basically make use of bigger stencil and compare more derivative terms in your Taylor series expansions and get more higher order accurate system. So, what we are doing in the compact scheme is that we are comparing the higher order derivatives in the Taylor series on the left and right hand side, and we are computing the coefficients. So, for the same stencil, we are getting basically more accuracy, right, by comparing the higher order terms. For example, for the compact 4 scheme, which is the 3-point stencil system, we compared the first derivative and the third derivative on the left hand side and right hand side, and we got the value of alpha n a. Okay. So, we can increase the stencil size, compare more higher order derivatives and get more accurate schemes. So, for example, today we are going to look at the compact 6 scheme. Okay. So, this is the 6th order compact scheme. So, in this particular case, you can have a grid. So, this is your grid, okay. Use a black color. This is I plus 1, I minus 1, I plus 2 and I minus 2, right. So, what we are going to do? We are going to use all these 5 points to compute our derivatives at these 3 points. Okay. So, you can use the 5 points also, I mean in the derivative on the left side also, but that will create a pentadiagonal system and that will become even more expensive to compute, right. So, what we are going to do on the left hand side, keep only the I minus 1, I and I plus 1, on right hand side we can use the 5-point stencil. So, that will become alpha phi I minus 1 prime plus phi I prime plus alpha phi I plus 1 prime will be, now we will have 2 unknowns. So, one will say A, this is phi I plus 1 minus phi I minus 1 by 2 h, and this you can quickly recognize why I am using 2, and then you will have B phi I plus 2 minus phi I minus 2 by 4 h, right, because when you are using this I minus 1 and I plus 1, the distance between among these is 2 h and this is basically 4 h. So, that will anyway come out. So, you can use it like this, and then what you need to do, you need to use the Taylor series expansion for all these points I plus 1, I minus 1, I plus 2, I minus 2, I phi prime I minus 1 and phi prime I plus 1, okay. And then you have to compare the coefficients on both on side of phi I prime, phi I triple prime and phi I fifth prime, okay, which is basically del phi by del x I del q phi by del x q at I and del phi phi by del x phi by at I. Okay. So, if you compare this, you will get 3 equations, okay. One corresponding to this, another to this, and to this, and you have 3 unknowns which are alpha, a and b, okay. And you can make the computations and you will get the value which is basically 1 by 3, 14 by 9 and 1 by 9, right. So, this you can see that is quickly becomes very tedious to make the hand calculation, but you can use Mathematica or any symbolic software or even the MATLAB to get these values. So, you just write these 3 equations, compare the left hand side and right hand side, and you will get these 3 values. You can basically write a code in MATLAB also. Okay. It's very easy. Okay. The other thing that I want to tell you is that you can have a trivial thing which is the explicit system. So, set alpha equal to 0, right. If you set alpha equal to 0, these terms will vanish, and then you can use your regular general discretization approach, okay. And you can compare your basically right now you need one a and b. So, you can compare your the first derivative and the third derivative, okay, and then you will get this 4 equal to 4 by 3 and b equal to minus 1 by 3. So, this is your explicit 4th order scheme and this is your implicit 6th order compact scheme. So, you can see that using the same stencil I minus 2, I minus 1, I plus 1 and I plus 2, you can get a higher order accurate scheme. Let us say you want even more accuracy. So, what you can do, you can consider this I plus 3 and I minus 3 as well, okay. And then your equations will change like plus c phi I plus 3 minus phi I minus 3 by 6 h, okay. And then you have to compare this del 7 phi by del x 5, okay, at I, okay. So, you have 4 unknowns now a, b, c and alpha, and you have 4 equations pertaining to all these 4 things, and you can get these values of alpha, a, b and c, right. And you have the 8th order compact scheme, right. Similarly, you can keep on increasing the stencil size and you can have the 10th order compact scheme, 12th order compact scheme, right. So, this is how you can increase your order of accuracy, but remember it comes at a cost. If you increase the stencil size, the computation cost increases, right. So, typically in the computations you the 4th order and the 6th order compact schemes are very popular. Okay. One thing that I have not discussed here is that compact schemes by itself despite being accurate they are not stable. So, you need to have a filter, okay. They are called compact filters. So, we will probably discuss these compact filters at a later point, but for now I want to leave you with a thought that for a given stencil you can increase the order of accuracy by making the system implicit, okay. And these schemes are called the compact schemes. So, this is just a comparison. This is these 2 are 3 point stencils and these are 5 point stencils, okay. And these are the coefficients that we have got for alpha, a and b, okay. We have discussed earlier, and you can see this is the trailing edge error. For the CD2 you have this h square, and for the compact you have h4, right. So, this is the 2nd order accurate system and this is the 4th order accurate system, but stencil point remains the same, the number of points in the stencil remain the same. And if you compare the CD4 and compact 6, they both you require 5 point stencil, okay. But the order of accuracy in the CD4 is 4 and for the compact it is 6, right. So, that is why compact schemes are more accurate, okay. And some finishing thought that the compact schemes provide better accuracy than the explicit schemes on the same stencil, but are computationally more expensive. The reason for that is that leads to a banded system and which needs to be inverted or solved using a TDMA solver, tridiagonal matrix solver, or some you might have read about the Thomas algorithms, okay. Basically, you use the forward substitution and backward substitution and calculate it, okay. These schemes are not very good with GPUs, for example, right. So, GPUs require your system to be highly parallelizable, but these systems are not highly parallelizable. So, you need basically special techniques, although there are some solvers, TDMA solvers already implemented in some of the CUDA libraries in NVIDIA, but generally these are not as good compared to let us say other schemes which are not implicit. Okay. Precisely because you have a matrix here which needs to be inverted, and it is a very costly affair. Let us say if your grid size is very large, your matrix size will be very large, and inverting that matrix is not that easy. Okay. And the last thing is that at the boundary, so let us say this is your boundary point, okay, 1 to n, and you want to calculate this the compact scheme at 2. Okay, these are the boundary values are known, but you want to get the value at 2, right. So, you have only 2 points 1 and 3 available. So, right, there is nothing on the left here and nothing on the right here. So, maximum that you can use is basically compact 4 here. Okay. Even if you might be using compact 8 or compact 6 at the other points, at point 2 you can maximum use your compact 4 schemes, right. And the other way to do it is basically use the one sided stencil. That means, like you want to calculate the value at 2, but use the points at 2, 3 and 4 for example, or basically maybe 2, 3, 4 and 1. Okay. So, that will give you one sided I mean you need to use the one sided formulation for the compact schemes, but practically speaking even if you use a one sided compact scheme or you lower the order near the boundary, it does not make much of a difference. So, and more practical way is that as you come towards the boundary from your internal points, you decrease the order. Okay. So, you might want to use the 4th order here, 6th order here, and other places you can might want to use the 8th order scheme. Okay. So, reduce the order of the scheme or use the one sided compact scheme. I have not discussed the one sided compact scheme derivation, but you can do it like we have been doing for the two sided scheme. Okay. Only thing is that the symmetry argument that you have been making to reduce the number of coefficients will not be applicable when you use the one sided scheme. Okay. So, this finishes our discussion on the compact scheme. One last thing I want to touch upon in terms of discretization is the non-uniform discretization. So, very often your grid will not be uniform. For example, let us say if you want to calculate something on a flat plate. Okay. So, you will have the boundary layer which is developing, okay, like this, and you want to capture the events very close to the wall in the boundary layer very well, and outside anyway you know that the flow is not that vertical, you might use the Euler equation also, even the Bernoulli equation will be fine, but here there are a lot of things which is happening, your boundary, your velocity is changing very quickly. Okay. So, all these things are happening here, right. So, in order to capture this behavior well, what you need to do? You need to make very fine mesh close to the boundary layer. So, this is called the boundary layer meshing, right, and then as you go up basically you can reduce the number of points, right. So, this is a very common approach in CFD. So, this is called the boundary layer meshing, right. So, you have boundary layer meshing. So, you have very close points near the wall, and as you go away from the wall the points basically become coarse, right. So, in order to handle this kind of situation, let us say if you are going to use the finite difference formulation. So, this delta x is different from let us say this delta x. Okay. So, you have one on this distance and another let us say here, okay, and thus the ratio between the two is called the stretching ratio. So, you can call it if this is I and this is I plus 1 and this is I minus 1, right. So, you can call this as a delta x I, and this is your delta x I plus 1, and similarly delta x I plus 2 will be different, delta x I plus 3 will be different, right. So, delta x I is equal to x I minus x I minus 1, and delta x I plus 1 is will be x I plus 1 minus x I. Okay. And the task is to find this gradient at I, point I. So, how do we do that? Okay. We will use our good old approach that we had is so you have f I plus 1, the Taylor series approach. So, remember this I I plus 1 and I minus 1. Okay. So, this is delta x I plus 1 and this is delta x I. Okay. So, you will have f I plus delta x I plus 1 f prime I plus delta x I plus 1 square by factorial 2 f prime I plus delta x I plus 1 q by factorial 3 f I triple prime and so on and so forth. F I minus 1 will be f I minus delta x I, right. Here it is I plus 1, but here it is delta x I, okay, minus f I prime plus delta x I square by factorial 2 f I double prime minus delta x I plus 1 cube by factorial 3 f I triple prime. Okay. This is your 1 and this is your 2. So, do 1 minus 2, that will be f I plus 1 minus f I minus 1, this will be cancelled, will be equal to delta x I plus 1 plus delta x I, right, f I prime. And earlier when we had uniform mesh, this used to get cancelled, but this time it will not get cancelled, and this will become delta x I plus 1 square minus delta x I square by 2 f I double prime, and then we will have other terms, right. So, you rearrange it, take f I prime will become f I plus 1 minus f I minus 1 by delta x I plus 1 delta x I, okay, minus. So, this is a square minus b square, and this is a plus b. So, that will become a minus b, that is minus delta x I minus I plus 1 minus delta x I by 2 f I double prime plus other terms, and this delta x I plus 1 and delta x I, the summation of these two. So, this is delta x I plus 1 is equal to x I plus 1 minus x I, and delta x I is basically x I minus x I minus 1. If you add these two, so that will become x I plus 1 minus x I minus 1, right. So, this will become f I plus 1 minus f I minus 1 by x I plus 1 minus x I minus 1 and minus delta x I plus 1 minus delta x I by 2 f I double prime and plus other terms, right. So, we can calculate a derivative like this, but you can quickly notice that here we have used the central differencing approach. We consider this I plus 1 and I minus 1 both, but despite that our the first the accuracy is here goes as delta x or h, right, if you want like that. So, that means it is first order accurate. So, despite using 3-point stencil and the two-sided formulation, we got the scheme which is the first order accurate. So, because of the non-uniform mesh, these terms do not cancel out, okay, and that is why your order of accuracy goes down. So, this is a very common thing you will be hearing, that when you use a non-uniform mesh, your order of accuracy goes down compared to when you use a uniform mesh, right. But sometimes you do not have a choice, as I told you that let us say near the boundary layer you have to use stretching, okay, because the things are changing very fast, and away from the boundary layer the things the events are not that interesting. So, you are not that interested in that. So, if you use uniform mesh in the entire thing, your grid size will be very huge, because the minimum grid size that you require near the boundary layer is very small, right, and you do not want to use the same grid size away from the boundary layer also. Okay. So, despite of the fact that your order of accuracy goes down, you need to basically use the non-uniform mesh, right. So, this is the same thing is on here. Okay. So, now one question comes that the compact scheme that we have derived is for the uniform mesh. So, how do we use the non-uniform mesh, I mean compact scheme for the non-uniform mesh, okay, or even for let us say for meshes which are not very nicely aligned. For example, if you want to do flow over an aerofoil, right. So, this is your aerofoil, your mesh will look like this, okay. something like this, okay. And then your mesh will look something like this, right. The center one is your aerofoil, okay. So, can we use basically our compact scheme or whatever finite difference that we have discretization that we have discussed, can we use on these kind of systems, right. But because all of the things that we have discussed is basically for the uniform mesh, okay, on a Cartesian system, let us say x y or x y and g, okay, where things are changing very smoothly and uniformly, right. But we can use those formulation or all those ideas on a non-uniform mesh or even a mesh like this by doing something called curvilinear transformation. Okay. That means, basically even if your things are changing very rapidly, right, you can basically convert it into a uniform mesh, okay, by using a Jacobian, right. So, from this mesh which is changing basically rapidly, and this is a uniform mesh, so this is a non-uniform mesh, and this is your uniform mesh. So, between that you can use a transformation, you will get a Jacobian which basically maps each grid point to the grid point in the uniform mesh. But the advantage is that you can use all your derivations on the compact schemes on this uniform mesh, calculate the metric, grid metric, Jacobians, do the calculation of uniform mesh and do the back transformation and get back to your non-uniform mesh, right. So, you can use your higher order schemes by doing this transformation. Similarly, if you have a complicated grid like this, not very complicated, but a grid which is closed, okay, like in a curvilinear system, we can use the transformation and use the same ideas that we discussed for the discretization. Okay. So, we will be discussing the curvilinear transformation in the later classes. So, for today we will finish with the thought that we can approximate a function derivative using a numerical approach, and you have many different ways of getting the discretization. You can have the central differencing or the compact scheme or the one sided formulation, and they all approximate the derivative in a different way, and you have different orders of accuracy for those schemes. And we have seen some examples where we saw that how the compact schemes are doing better than the regular schemes, right. But we need to discuss about the stability issues also, that we will be discussing in the next classes. So, first we will start with the model equations like the convection equation, diffusion equation and convection diffusion equation, and solve very simple problems on that, okay, using the discretization approaches that we have discussed. Okay. After that we will go to the stability and the accuracy, consistency, robustness and all this kind of things. How do you know that how the solution is going to converge or not? So, all these things we are going to discuss. Okay. And then we will also look at the curvilinear transformation at a later point of time. So, with that we will finish the discussion today. See you in the next class. Thank you.